Hello and welcome to the Module 1 third video, GPIO, General Purpose Input Output. Here you will learn how to use the ports for connecting devices to your Raspberry like sensors and actuators. The GPIO are these pins over here. They are a physical interface between the Pi and the outside world. At the simplest level, you can think of them as switches that you can turn on or off as inputs, or that the Pi can turn on or off as outputs. Of the 40 pins, 26 are GPIO pins in yellow, and the others are power, orange and red, orange 3.3 volts and red 5 volts, and ground in black, plus 2 special pins for EEPROM communication, which you should not play with unless you know your stuff, really. A more detailed view is on the right, in this table. When programming the GPIO pins, there are two different ways to refer to them: GPIO numbering and physical numbering. This is general GPIO numbering and this physical numbering. GPIO numbering, or VCM, are the GPIO pins as a computer sees them. The numbers don't make any sense to humans, they jump about all over the place, so there is no easy way to remember them. Physical numbering, on the other hand, refer to the pins by simply counting across and down from pin 1 at the top left. Beginners may find the physical numbering system simpler, but generally we recommend using the GPIO numbering. It's a good practice and most resources use this system. Most pins can be configured as digital input or output. A digital input means that the Raspberry is able to know if what we have connected to the pin produces 3.3 volts, a high value, or 0 volts, a low value. And a digital output means that the Raspberry can produce 3.3 volts, for example to switch on a light, or 0 volts to switch it off. Inputs may come from a sensor or other device, and outputs can go to an actuator, slide, or motor, or other device. So GPIO voltage levels are 3.3 volts, okay, and not 5 volts tolerant. These are 3.3 volt logic pins. A voltage near 3.3 volts is thus interpreted as a logic 1, while a voltage near 0 volts is a logic 0. The input pins are configured by default to sync at most 8 milliamperes. Be very careful with these values. Some of the pins have special purpose, for example, serial communication, I2C communication, etc. We will see them later. More information about the pinout can be found at this address over here. So, how do we use a GPIO? It's very easy, especially programming with Python. Although we will cover Python programming in the next module, we will have a brief introduction here to work with the GPIO. In order to use the GPIO, you just have to create a file in a text editor. Write a header to use the GPIO, and then write your code over here. Save your file, your text file, as a .py, and then execute in the terminal python your file.py, and it will execute. That is all. Now we will see a couple of examples. To switch on a LED and detect a button pressed. To switch on a LED, we have to connect one pin of the LED through a resistor to a GPIO pin of the Raspberry and the other pin to ground. So we have one pin through a resistor to ground in this case, and the other one to input, physical input number 7. It's 1, 3, 5, and 7. Please be very careful anytime you connect anything to the Raspberry. To specify the pin number, we have two choices as explained before, GPIO numbering or physical numbering. To select any of them, use this instruction. GPIO.setMode board for physical layout and BCM for GPIO layout. So, in first place we have to import the library, then set the mode. In this case we use physical numbering. Then we have to configure the GPIO pin as output with instruction GPIO setup as output, pin number 7. And finally we switch it on with this instruction output to true, or switch it off if we write false here. We can use the same principle with any device that can be switched on and off, like a ventilator, motor, etc. Okay, let's see how to do it. I already have two files with the code to switch the LED on and off. We see here true and false. And I have my LED connected here to the Raspberry. So we open a terminal, we move to the desktop where I have my files, and I do Python 3 LED on.py, and the LED switches on. If I execute LED off, it switches off. On again and off again. Now we are going to use the inputs. We're going to connect a button. In this case, we connect one pin of the button to the GPIO pin and the other to ground. As we see in this example, one pin to the ground and the other one to an input. In this case, we choose this pin that in the GPIO format is pin number 18. Okay, in physical would be 2, 4, 6, 8, 10, and 12. When we press the button, the GPIO input will read a 0, and when we release, the GPIO input will read a 1. But will it? No. Why? Because when the button is not pressed, the GPIO pin is not connected. It is floating. To solve this problem, the Raspberry has one thing called pull-up resistors. It connects the pin to power through a resistor, as we see in this diagram at the bottom of the page. We have the button over here. When we press the button, we put a 0 to the microcontroller, and when we don't press the button, we get a 1 VCC or power into the microcontroller. The same happens with pull-down resistors. The button is connected to power, and the GPIO pin has a pull-down resistor to ground. The code that we use is here on the screen. In this case, we configure pin 18 as input with a pull-up resistor. 18 input and pull-up resistor. When we press the button, a message is displayed in the terminal. We check the input when it's false, because we press the button and we get a 0, then a message is displayed. So we use pull-up for pull-up resistors and pull-down for pull-down. We can use the same principle with a movement detector or a window or door open-close detector. Okay, now we are going to test our program. I have the program written here in this file, BCM, you choose the GPIO 18 as an input, and we choose a pull-up resistor. Here we make a while loop. We keep reading the input 18, and when the input is false, that means that we have pressed the button. Then we write on the screen button press, then we wait a little bit. We can test it. In the same way, now the program is waiting for us to press the button. We can go and press, okay, button press. If we keep pressing, okay, it's writing all the time. We can change a little bit the time here. For example, 2 seconds. We save it. So we close it, and then it's ready to run again. We press, then we keep pressing. It waits a couple of seconds. Okay. To close it, we press Ctrl+C, and we're set up. A special pin is used for the one-wire bus. A one-wire is a device communication bus system designed by Dallas Semiconductor that provides low-speed data signaling and power over a single conductor. One wire is similar in concept to I2C, I2C, but with lower data rates and longer range. It is typically used to communicate with small and expensive devices such as digital thermometers and weather instruments. In one-wire sensors, all data is sent through one wire, which makes it great for microcontrollers such as the Raspberry Pi, as it only requires one GPIO pin for sensing. For example, we have a temperature sensor over here, and we connect it here to one pin. We have also ground, and this is ground, and this is power, but we need only one wire to get the information. In addition to this, most one-wire sensors will come with a unique serial code, which means you can connect multiple units up to one microcontroller without them interfering with each other. We could place another one here and connect the pins, and it will work as well. In the Raspberry, one wire works in pin 7, GPIO 4. This is the one wire GPIO pin. We will use it for connecting temperature sensors, as in this image, and we will learn more on this in module 4. Let's talk about serial communications. Other special pins are used for serial communication buses like I2C, SPI, and UART. All of them are used to send data to other devices. What does it mean, serial communication? Serial communication is an umbrella word for all that is time division multiplexed. It means that the data is sent spread over time, most often one single bit after another. We have UART, Universal Asynchronous Receiver Transmitter, one of the most used serial protocols. We have SPI as well, SPI 0 and SPI 1. Serial Peripheral Interface, another very simple serial protocol that is synchronous and master-slave. And I2C, Interintegrated Circuit, pronounced I2C or I2C, Also synchronous protocol master-slave, but it uses only 2 wires. You will use one or another depending on the device you are connecting to. So, that's all. In this lesson, we have learned how to use the input and output ports of our Raspberry, the GPIO, how to access them, how to configure them, the different protocols that are available, and that we will use in Module 4. And we have made 2 examples to introduce the GPIO. I hope you like it and see you in the next lesson.